on the next chapter of current electricity. So far we have discussed electrostatics and applications of electrostatics. Now we are going to look at flowing charges. Every material has some kind of electrons, whether they are free or fixed. But these number of electrons which are free, based on that we can divide the materials in three types. So the materials which have a large number of free electrons, they are called conductors. Now when we say free electrons, those electrons are free in the sense that they cannot be assigned to a particular atom of the conductor. So you got some material, and in that material there are billions of atoms, and then of course every atom contains many electrons, but out of all these electrons connected or part of each atom, only the outer shell electrons they get free. In other words, they are very loosely bound to that atom. So we are not saying that all the electrons are free or unattached to an atom. We are saying only few of the electrons are free from each atom. So in other words, there are materials where there are still very large number of free electrons available. You cannot assign them to any particular atom. Such material is called conductor. Then there are materials where there are no free electrons. All the electrons are perfectly bound, hard bound to the atom, even the outer shell electrons. As a result, such materials do not have any free electrons, and then those materials are called insulators. Then there is third class of materials, which is semiconductors. They do have some free electrons, but the number of free electrons in semiconductors is not as much as conductors, but it is somewhat above the insulators in the sense there are certain free electrons, but not as many as conductors. So semiconductors have properties which are in between conductors and insulators. Now out of these three types, in this chapter we are going to consider only the conductors. So in conductors, these free electrons, they are not at rest, they are moving about randomly. So you can imagine that this is we are inside a conductor, and inside the conductor there are atoms which are fixed at fixed locations. Those atoms are not moving, but the electrons which are free, they are moving everywhere in this region. They are moving because they have thermal energy, and because they have thermal energy, that is basically coming from the outside or surrounding or the temperature of the material, that temperature of the material is understood, or that temperature of the material gives that thermal energy to the electrons, and then those electrons are moving absolutely randomly. So if you observe an electron moving inside the conductor, you will find that electron is pretty much moving randomly like this. So you can see that there is no preferred direction, there is no preferred particular way in which it will go. It will absolutely move randomly in this manner. So an electron in general moves randomly. Why does it change its path? Because every electron is moving randomly. So all these randomly moving electrons collide with each other, but at the same time they also collide with atoms of the conductor. Now when they collide with atoms of the conductor, they have to undergo they almost stop momentarily, and they stop momentarily and again they change their path. So what is happening here, an electron collides with atom, electron almost stops and then changes its path, and then again it starts moving, and this is the picture we are having here. So the idea is that since the motion of the electron is random, there is no electric current. So we need to understand that electric current is not only motion of charges, electric current is a directed motion of charges. In other words, that motion of charges that must have a particular direction, a particular flow, and if there is no particular direction, then motion of charges does not really constitute electric current. Hence, even though you have random motion of billions of free electrons, this will not give you electric current. So you can hold a lump of copper in your hand and there is no electric current in that, although the electrons are moving randomly there. Now suppose I got a rod like that, and this is a conductor rod, and in that conductor rod all these electrons are moving randomly as we show there. But suppose I generate an electric field inside this conductor. Suppose there is a mechanism by which I generate or apply an electric field here, and if I apply an electric field like this, then we know electrons are always moving opposite to the electric field. So what happens that these electrons, they are moving randomly. This random motion, by the way, is called thermal motion. It's not like the moment we keep this switch on the electric field, they all stop and start marching in that direction because they must go in the direction opposite to electric current. It's not like that. What happens is this motion continues, this random motion, but now this apparently random thermal motion, it now develops a direction. In other words, you will find the electron does appear to move like this still, but eventually you will find that it has come to this particular point. So it does appear to move randomly like that, but now it has come here. Again, if you observe it for some more time, you will find that it still continues to move randomly, apparently at least. And then you will find that it has come to this particular point. So now you understand that the electron is slowly moving this side. This motion of the electron where it is appearing to move randomly, but now there is a preferred direction of motion. Such a motion is called drift of electrons. So this is the drift motion. And this is very much different than the marching motion of soldiers, where all the soldiers suddenly stop and stand still and start moving in one direction. This motion is directed motion, but it is also having a thermal random motion. So you could imagine it in this way, that there is a thermal random motion, and on that thermal random motion there is a directed motion superimposed. So the motion of the electron is happening in this manner. So you can see that these electrons are drifting in that direction. If you observe these electrons for a long time, and in that long time, if the distance they travel like this is L, which is called the drift of the electrons. So over a long time, if the distance traveled by the electrons in this way is L, and the time taken is t, then we define a quantity called drift speed, and drift speed is defined in this manner, Vd, and that is simply L by t. So this is a very important quantity in our analysis of electric current, Vd, which is drift speed, which is L by t. Where L is some over a long period of time, you observe that distance L, and then that L by t gives you the drift speed. In other words, it's kind of an average speed we are discussing here. Now let us come back to this conducting rod. Then the question arises, how are you going to apply that electric field there? And the way we are going to apply the electric field is simple. We are going to connect a battery to it. So here's a connected battery to this conductor. This battery has a voltage V, and the moment you connect that battery like that, this rod will develop an electric field in that direction, and that electric field will be continuously maintained by the cell. So the cell is there to maintain that electric field through the conductor. As a result, now electrons will start drifting in that direction, and this is the discussion we are going to have. There are few quantities we need to now define though. So the first quantity that we define is this L0, where L0 is the average distance between two collisions, two successive collisions of course. And similarly, tau is the average time between two successive collisions of electrons. So we now realize L0 is the average distance between two successive collisions, whereas tau is the average time between that or for that motion L naught, then by using kinematical equations we can write S equal to ut plus half at square. We saw that the electron collides with atom but it almost comes to rest. That means the motion, you can effectively say, starts with zero initial velocity. So the initial velocity of the electron when it undergoes from one point to other point and then it undergoes a collision here to there, that it starts with zero velocity. Thus we write an equation of the kind L naught equal to ut, which is 0, plus half at square. So ut 0 plus half a. Now the acceleration simply is the force divided by mass. The force acting on electron is charge times electric field. So this is the force acting on the electron, charge times the electric field, divided by the mass of the electron in E, and that multiplied by tau square. So we now get a quantity L naught by tau, but L naught by tau by definition will become the drift speed. So this will become drift speed Vd, and that turns out to be equal to E tau divided by 2me multiplied by the electric field, like this. So we will maintain this quantity. It is an important quantity, and we'll call this equation 1. So that is one result we have obtained there. Now there's another quantity we can talk about. This is called N. N is the number density of free electrons, and that means it is the number of free electrons per unit volume. Number of free electrons per unit volume, hence its SI unit of this quantity will be simply per meter cube. So imagine in this conductor there is a density of free electrons, number density, how many free electrons per unit cube per unit volume, that is this. And then suppose there is a charge Q in this conductor. So there are total charge Q in this. When I say charge, of course I mean only the free electrons. So imagine that the total free charge in this conductor is Q. Then this total charge Q can be written as the number density multiplied by the charge on each particle. So please understand, I am discussing the total free charge in this rod, which will be obtained by number density multiplied by charge and multiplied by volume of the rod, because this is per unit volume. So Ne multiplied by the volume, and that volume is A times L, where A is the cross-sectional area of the conductor. Now imagine that when I start applying this electric field by the battery, this charge Q, the free electrons, they should all go in this direction. Let's say the time taken for all these charges to go this much distance L is time t. So imagine now that this charge must travel here, so that new charge coming from the battery will take its place. So this charge continues to go like that. So this charge Q will take time t to go all the way through the rod. I will divide by that time t. So when I divide both sides by t, therefore I'll get the result Q by t is equal to N E A L by t. But now immediately I see that the left hand side is nothing but the charge flowed per unit time. So the left hand side is nothing but the current. That is how we define the current, the rate of flow of charge. So the charge that flowed was Q, the time taken was t. So the left hand side becomes electric current I, and then the right hand side is Ne, but then L by t, as we all know, is nothing but the drift speed. So we'll use that L by t as the drift speed, and thus we get this quantity Ne Vd multiplied by A. Then we define another quantity I divided by A, and that is defined as current density, which is current per unit area, and that current density is used or denoted by letter J. Just one thing though, we must understand which area do we take. We take the area of cross section of the conductor perpendicular to the flow of current. So A perpendicular is always this. And thus, in other words, if I want to figure out how much is the current flowing through a small area, then di always will be obtained by J dot ds, where ds is the surface area vector. So that dot product must be there. That dot product will ensure that the area we are taking is perpendicular to the flow of current. So di, a small current, is passing through some area ds is always obtained by J dot ds, and in other words, if I want to figure out the total current I, it can always be written as J dot ds integrated. But the point to be noted is J, the current density, is a vector quantity, which is very interesting again, because current itself is a scalar, but J, current density, is a vector quantity, and then when you do the dot product of area through which the current is passing and that J, that dot product will give you I, and in other words, I divided by area perpendicular is current density J. SI unit of that quantity, as you can immediately see, is ampere per meter square. It's ampere per meter square. So, having defined that current density, now that equation therefore becomes I by A is equal to J, which is equal to NEVD, and this is a very, very important equation in current electricity. Current density is given by NEVD. Very important, very fundamental. We'll go ahead with this and we will write that J as NE, but then we have established already VD, equation 1. So here you go, equation 1 tells me that it is equal to that. So this will give me NE squared tau divided by 2ME multiplied by the electric field E. This, as I point out, using equation 1. Now, if I look at that, and if I look at this particular quantity here, then the bracketed quantity, see, charge is a universal constant, mass of electron is a constant anyway, but the small n, which is the number density, and tau, which is the average time between two successive collisions, these two quantities, small n and tau, they will depend on the material chosen. For example, copper will have a different number density, aluminium will have a different number density. Same manner, copper will have a different average time between two collisions, and aluminium will have a different average time between two collisions. So, this bracket simply depends on the material Not only that, let's understand it in a little bit detailed manner. Imagine you got a material where number density is very high, and if the number density is very high, that means you have got many free electrons. So if the number density is high, then that material must be a good conductor of electricity. Then on the same way, if you have high tau or high average time between the collisions, which indicates that after undergoing first collision here, the electron goes unhindered for a long time like that, and that means again that makes it a better conductor. So having a motion of electron which is bouncing too many times like that, and having a motion of electron which goes like this and then bounces, obviously the second case is a better conductor of electricity. That means having higher value of N, having higher value of tau makes the conductor or makes the material a better conductor, and therefore this bracket is called conductivity, because this bracket Having high value indicates that the material is able to conduct electricity better. So the ability to conduct electricity is obtained from this bracket, and that is a property of the material, and hence that bracket whole is called sigma, and that is conductivity. As we saw, conductivity is a property of the material. The SI unit of conductivity is Siemens. And this equation, J equal to sigma E, is the second fundamental equation of current electricity. The first one was J equal to NEVD. The second one is J equal to sigma E, and where sigma stands for conductivity of the material.